Welcome to lab number 9. In this lab, we're going to deal with topics from chapter 7 of the textbook related to musculoskeletal levers in your body. But before we do, I'd like to briefly summarize some of the things we learned in last week's lab, checkoff number 2, related to the 3 cardiovascular diseases that we modeled, starting with hypovolemia. Hypovolemia is the severe loss of blood from your blood reservoir in your body, due maybe to an internal aneurysm for internal bleeding or external bleeding due to a severe cut or an accident. And if you have less blood in your blood volume, then of course your cardiac output is going to decrease and your blood pressure will also decrease. The question is, how much blood can you lose before it becomes dangerous? If you go to the Red Cross, you'll donate a pint of blood, and they'll give you a cookie and a drink and have you rest for a bit, but most people won't feel that significantly. A pint is half of a quart, and a quart is about the same size as a liter. So you've donated half a liter of blood. Well, that's about 10% of your total blood volume, because most people have about 5 liters of blood total in their body. And that's not too significant to donate 10%. If you were to donate 2 pints of blood, then you'd start to feel it. If you lose 2 liters of blood, that's 40% of your blood volume, then your cardiac output and your blood pressure would be so low that you'd be in severe danger. Now, related to left heart failure, we have 2 parameters in our model related to the strength of the heart. There's CHD, which is up here, and CHS, which is here. You want CHD to be high because you want the heart to be very compliant and soft so that it will relax and allow blood to easily fill during diastole into the left ventricle. But on the other hand, during systole, you want the heart to squeeze very tightly to eject the blood, and that represents a very low compliance. Well, if there's a ratio of 15 or greater between CHD and CHS, that represents a healthy, strong heart. Anything that causes those two to come closer together represents a weaker heart. What would cause that? Well, if you were to have a heart attack and some of your heart muscle were not to get enough oxygen, some of the muscle would die and it couldn't squeeze as tightly, and that would raise CHS. If they get too close, that would be systolic left heart failure. On the other hand, if your heart works against high blood pressure for many years, the walls of your heart may become very thick, and just like a thick-walled balloon, it can't relax as easily, and that would bring CHD down. And once again, if it gets too close to CHS, that's diastolic left heart failure. If the ratio between CHD and CHS is 10 or less, then you're into severe heart failure. And of course, when these two are even, your heart is gone completely. Now, anaphylaxis. Anaphylactic shock is where a person is severely allergic to allergens such as a bee sting or perhaps a food allergy such as peanuts. And what happens in anaphylactic shock is that the sympathetic nerve system relaxes, and all of the muscle around the vessels in your body suddenly relax. Normally, these muscles are slightly tight, representing muscle tone, vascular tone, for redistributing blood in your body. If they suddenly relax, then your blood volume is pooled and it won't circulate around as much. That's represented by flushing in your face and a drop in cardiac output and in blood pressure. People who know that they may be subject to anaphylactic shock carry around with them an EpiPen. This is an injectable dose of epinephrine or adrenaline that they will inject immediately if they feel that they're going into anaphylactic shock. What does that do? That tightens back up the smooth muscle around all the vessels and brings their blood pressure and their cardiac output back up. So how did we model anaphylaxis? Well, all of the smooth muscle around all of your vessels relaxes, which means that the compliance of all of your vessels increases. I chose just one, the compliance of the veins, because that's where most of the blood is. And the compliance of the veins doesn't have to increase very much to represent pooling of blood in the veins, dropping your cardiac output and dropping your blood pressure. Now, on to this week's lab. Now let's do the first part of today's lab. We're going to do some detective work on the internet to find examples of each of the 3 classes of levers that occur inside the human body, class 1, class 2, and class 3. Let me remind you what the definition of each of those classes of levers is. Here's a figure from the textbook. Class 1 is defined as when the weight and the force are on opposite sides of each other from the pivot point, or the fulcrum, where the force is produced by the muscle. This is sometimes called the teeter-totter arrangement. For a class 2 lever, the weight and the force are both on the same side as each other from the pivot point, but the weight is closer to the pivot than the force. For a class 3 lever, again, the force and the weight are on the same side of the lever as each other, but here the force is closer to the fulcrum than the weight. Most of the lever arrangements in the body are class 3 levers for a reason that we'll cover later in the lab. So what you're going to do is you're going to find examples of each of those classes of levers in the body on the internet, and in this column you're going to put an anatomical sketch of that particular configuration. And what I mean by an anatomical sketch is something that looks maybe something like this. Now, it doesn't have to be this perfect. It just is a sketch that you can do your best of. But it includes the bone, which is the lever arm. It includes the muscle and the direction of the force of the muscle and the insertion into the bone. Label the muscle if you can. It will include the pivot point and show the location and direction of the weight that the muscle is supplying. That's the anatomical. Do the best you can on that. And then in the second column, you're going to put a free body diagram corresponding to the anatomical sketch configuration. And by free body diagram, we mean a stick diagram that looks something like this, where again you show the location and directions of each of the forces, including the joint force and the weight of the lever arm itself, or the bone itself. If you can, draw this stick that represents the bone with a ruler if possible. You're going to do that for each of the 3 classes of levers that you find inside the body, class 1, class 2, and class 3. Oh, and incidentally, for a class 3 lever example in the body, see if you can find something other than the biceps, if possible. You can use the biceps if necessary, but we're going to do the biceps later. So see if you can find another example of a class 3 lever other than the biceps. Please stop this video now and do those sketches before going on. Now, for the second part of this lab, we're going to actually do some experiments and make some measurements of a typical human biceps configuration. First, I'd like you to make a free body stick sketch of this situation with the arm held horizontally and with distances labeled on this sketch. We didn't label distances on the previous page. What I mean by a horizontal free body diagram of the biceps is given here. At the top is the anatomical diagram. We don't want to repeat that, but we do want to repeat the stick diagram, but make it more simple than this, because I'd like our calculations to be a little bit more simple than the more complex calculations for the homework. Make the arm being held in a horizontal fashion, like this. That means that each of the weights is vertical at 90 degrees with respect to the bone. That makes all these angles fall out of the equation, so you don't have to worry about angles. And the weight is also vertical. Let's make the angle that the muscle forms, the force of the muscle forms with respect to the bone, also at 90 degrees, so beta goes to 0. And then the joint force, let's make it vertical also, so theta goes to 90 degrees. Now we are, though, going to have to put in the various dimensions of the distances of these various weights and forces from the pivot point, which is the elbow in this particular case. Please draw that out, and what we'll do next is we'll find somebody, a typical human, and we'll make measurements to see if we can put some values into these lengths. We'll do that next. Now we have to find a human volunteer where we can measure some of the distances in the biceps configuration where the biceps insert into the radius. And I'm looking around here to find somebody, but there's nobody around. So I guess I'm going to have to volunteer. I'm hardly typical, but it's the best we can do. I'll be back in a minute. Well, here's your volunteer ready to be measured. But before we do, I'd like to explain why many of the musculoskeletal levers in your body are class 3. And I'll use the biceps muscle as an example. The biceps muscle is quite long from there to there. But like all muscles, it exerts its maximum efficient force only over a fraction of its resting length. Only over a distance, maybe a third of its resting length from contraction to extension. So, if the hand were attached directly to the bottom of that muscle, your hand could move over only a very limited range, something like that. But because of the lever arm of a class 3 lever, that allows much greater range of motion for your hand, increasing flexibility. Now the price you pay for that is that your biceps muscle has to exert maybe 5 to 6 times more force than the weight it's holding, but that's a price we're willing to pay. Next, I'm going to measure the distances from the fulcrum, which is the elbow, out to the point in my palm where I'm holding the weight. And I measure that to be 32 centimeters. Next, I want to measure the distance from the elbow to where the biceps muscle inserts into the radius. To do that, I'm going to flex my biceps muscle. Boy, that's not very impressive, but I can see that it inserts right about here. So to measure that distance, I get a distance of 6 centimeters. 6 centimeters. Mark those distances down on your worksheet. And then we have to account for somehow the weight of the bone. And just arbitrarily, I'm going to say that the weight of the bone has a weight of 30 grams, and it's located at a distance 20 centimeters from the pivot point, so that B is 20 centimeters. Please put that into your diagram. Now let me point out that we're now giving weights in units of grams, which are not strictly true, but if we assume a constant acceleration of gravity, oftentimes weights are given in units of grams. We just haven't multiplied and don't need to multiply by the acceleration of gravity. The weight that's going to be held in the hand is 200 grams. That will give us the weight W sub C. So I'll mark those on your diagram, and then we'll go on to calculate what we think the muscle force is going to be. Well, now that we have our stick diagram and we have our various values of distances and weights, we can calculate the muscle force F sub M and also the joint force F sub J. Remember, they're 90 degrees with respect to the bone. And we could do that in gram units, needed to hold the 200 gram weight. You balance the moments here, and that will allow you to find F sub M in grams. And then you sum the vertical forces here, and that will allow you to find the joint force, again in grams. Please do that before we go on to make the actual measurements in a simple model of this arrangement. I'll show you that next. I've assembled a simple model here that will allow us to actually measure the amount of force to raise that weight that we just calculated. And I'm using the same distances that we used in the calculation. Here's the pivot point, which is the elbow, and the distance from the pivot point out to the weight is 32 centimeters. The distance from the pivot point to where the biceps muscle inserts, and we're going to use this spring scale to represent the biceps muscle, is 6 centimeters. Let's see how much force it takes to raise that weight up and hold it in a horizontal position. Well, the scale reads exactly 1100 grams, 1100 grams. Oh, and notice with my left hand, I'm having to hold down on that pivot point with a lot of force. The joint force is trying to raise up vertically with a force that I would say is almost 1,000 grams, close to what we calculated. Now that we've measured the muscle force in our simple model, please put that value in grams down in this location here. And then to compare it to the calculated value that we thought we were going to get calculated from here, please do a percent difference between the calculated value and the measured value using an equation we've used several times in this class, and put that percent difference down here. They're probably going to be pretty close. And then, to finish up, get ready for a surprise, a Class 2 lever reveal. Let's finish up this lab by investigating something a little deeper, namely the Class 2 levers that many of you found on the internet to be represented by a ballerina on her toes or a person standing on their tiptoes. I've made a simple model of that arrangement here, where I have a foot here with the toe on the ground. Here is the ankle, the pivot point of the ankle. This tube here represents the femur with a weight representing somewhat the weight of the body. And then attached to the back of the heel is the gastrocnemius muscle, represented here by this spring scale. And we can measure on the spring scale how much force it takes to raise the heel off the ground with a weight of 405 grams on the bone. Let's see if that does represent a Class 2 lever. Now here I've assembled some equations which represents our model of the Class 2 lever standing on your toes. The pivot is where the toe pivots around the ground. Here is the femur, which represents the body weight in our model as 405 grams. And the gastrocnemius muscle is attached to the heel, and we're going to find the force of the muscle necessary to raise the heel off the ground. Here are the distances that I've measured on my model. When we balance out the moments, the clockwise moment is balanced by the counterclockwise moment. You solve for the force of the muscle, and you put that into your calculator, and you get 324 grams. Let's see if our model measures that amount. So this simple model seems to verify that standing on your toes is a Class 2 lever, because notice that this spring scale, which represents the gastrocnemius muscle, shows that for a 405 gram weight, the gastrocnemius muscle is exerting a force of about 325 grams, like we calculated. Oh, but hold it. Here's the surprise. This model is not the way your actual body is arranged, because notice that the top of the gastrocnemius muscle is attached to a post that's sitting on the ground. That's not the way your body is assembled. The gastrocnemius muscle in your body is actually attached to the femur, the very bone that it's trying to raise. And that turns this arrangement from a Class 2 lever into a Class 1 lever. Let me show you the mathematics for that. Well, we've just discovered that standing on your toes is a Class 2 lever only if the top of the gastrocnemius muscle is attached to a post that's sitting on the ground, and that's not the case in a real human. It's attached to the femur, and under those conditions, it translates the pivot point and moves it from the toe to the ankle, where the femur attaches to the foot through the tibia. And if you do now a balance of moments in that situation and solve for the force of the muscle, you get a much, much larger number, 1,620 grams. Let's see if our model actually measures that much. So let's reconfigure this simple model to represent the way your body is actually configured. Namely that the top of the gastrocnemius muscle is not attached to a post that's sitting on the ground, but rather it's attached to a point on the femur, the very bone it's trying to raise. So I'm now going to take the top of this spring scale, which represents the muscle, and attach it to a point on the bone itself. Wow, it takes a lot more force. And in fact, I can read on the scale that it's now taking more than 1,600 grams to support that weight, which is pretty close to the number that we calculated on the board. So this is indirect proof that standing on your toes is not a Class 2 lever, it's a Class 1 lever. So if on the first worksheet you have an example of a Class 2 lever of a person standing on their toes, please cross it out with a big X. No points will be taken off. What do we replace it with? Well, actually, I don't know of any Class 2 lever in the body that I've been able to find, so we'll leave that blank. I hope you've enjoyed and learned something about today's lab, and I look forward to having you in next week's lab.